Hi, I'm Brandon Hargis with NASA Langley Research Center and the Aerospace Education Services Project. I'm here to talk with you today about the Summer of Innovation module for engineering and the Thermal Protection Systems Engineering Design Challenge as part of the Challenges unit. In the training module today, I hope to provide an overview of the lesson's activities, to describe and show an illustration of the thermal protection systems apparatus that's used in the activity, and to provide some direction for successfully conducting the lesson's activities themselves. Your students are going to be challenged to build a thermal protection system that will protect a model of an Ares rocket from a source of heat for the longest period possible. The rocket will eventually fail, and a model that I'll show you in a few moments will fail in the glue joint between a wooden dowel and a brass screw. Now, a little background information that you may need and your students will gather as they continue working with this activity regarding heat and heat transfer. They are actually working on a challenge that's a real-world problem is faced by the space program, and that has to do with launching spacecraft and the heat and heat transfer that takes place while we're trying to protect the rocket structure, the components of the rocket, and the passengers or the cargo that may be on board that rocket. Heat is a form of energy that flows from a hotter place or a heat source to a cooler place, a heat sink. Heat transfer can take place in three ways. Conduction is when heat travels through a solid substance. Convection is when heat flows through a liquid or a gas. And radiation is when heat flows through empty space or a transparent medium. Your students are going to be working on a way to slow down the rate of heat transfer in order to protect the rocket or their Ares model rocket that they are given. There's different sources of heat on spacecraft, including atmospheric friction, engine exhaust, and hot particles. And to protect spacecraft, we have several different types of protection systems. Satellites can be protected with thermal blankets, as you see in the picture to the side of the gold thermal blankets, and Hubble recently received some new thermal blankets in Service Mission 4 a couple years ago, and that protects these satellites from the extreme heat and cold of space. Early spacecraft also used ablative heat shields like the Mercury capsule you see in the picture to the right. The ablative heat shield would have been found at the bottom of that capsule in the curved portion of the capsule itself. Ablate means to move away, and so in this case they're moving heat away from the spacecraft and the components and the people inside. A curved surface allows heat in the air to actually move the heat away in a quicker fashion. The shuttle program, we used reinforced carbon-carbon, tiles, foam, and felt blankets to protect the shuttle from the extreme heat that it comes in contact with during liftoff, as well as re-entering our atmosphere with atmospheric friction. And you can see in the pictures these tiles that have been applied to the shuttle, the heat-resistant tiles made of reinforced carbon-carbon. In future rocket systems, such as the Ares rockets, insulating foam can be used around the 5 liquid fuel engines that are found at the base of that rocket, and the thrust structures which attach the engines to the rocket itself are filled with this insulating foam. Now, the crew capsule Orion, which was built originally for the Ares 1 rocket, has incorporated the ablative heat shield, which we saw in the Mercury spacecraft, Mercury capsule picture from an earlier slide. This ablative heat shield moves heat away once again from the spacecraft, the components, and the people inside. Your students will be using a design process, engineering design process, as they complete this engineering design challenge. In groups of 3 or 4, they should be cooperating to complete the challenge, identifying a problem, which it will be given to them by you, the teacher. They will then brainstorm solutions to meet this challenge. Through their brainstorming processes, they may sketch out designs, illustrations, and labeling their designs, as well as looking for weak points in their design prior to actually building it. This is the point in which they would be using their creativity and their scientific knowledge to build a thermal protection system that will protect that rocket for the longest period of time. They should build their models, test and evaluate their models with your help, then share out their solutions and redesign. And this is the point at which the process repeats over and over throughout the remaining sessions. In the last session, they'll be presenting a storyboard and presentation, as well as providing you with a journal that they've kept throughout the process, where they marked down all of their design changes, made their sketches, and wrote down their solutions for redesigning their models. The design challenge is to build a thermal protection system using the specified materials that protect the model for the longest possible time. You can see on the right there is a figure showing the model of an Ares rocket that's built with a 1/4-inch dowel that has a hot glue applied to the end of that dowel. It can be applied either using a melting pot or a glue gun. Melting pots does seem to apply a little more even amount of glue, but glue guns are easy to use, and students can use them in the low temperature glue guns. Attaching a brass screw to that dowel using the glue, you can also see the hex nuts and washers that are used to attach their thermal protection system to the rocket itself. This is the portion of the rocket that will be receiving the heat from the flame, and you'll want to test this out ahead of time so that you can determine an appropriate distance from the flame so that you don't have smoking and fire taking place. The design constraints are that they only should use the specified materials to do their construction, that no glue can be used in their TPS because of course the glue could catch fire. No part of their thermal protection system can touch the dowel, and no part of the thermal protection system may touch the glue joint. So those are the constraints in their building. Now the test stand itself, you'll see here that this is a model that's built out of plywood, using a ring stand to hold the TPS model, and using a butane or propane torch to apply the heat as the heat source, apply the heat to the model itself. You notice in this figure that they do have a fire extinguisher and a bucket of water. Students should wear safety glasses, and tongs should be used to pick up the brass screw once their model experiences failure, and place that brass screw into the bucket of water so that immediately it begins to cool down. There are several safety hazards in doing this activity, and that includes working with an open flame, as well as working with hot metal, because the brass screws and the thermal protection systems will be hot after they've been tested in their experiment. In using the test stand, you can see in this figure there's much more information given, and in the guide you can have a list of all the materials used to build this test stand. But it's a simple piece of 3/4-inch plywood, using some other wood for a stop block and a base guide so that you can easily guide the ring stand along the wood. You do want this wood to be really smooth so that you have a smooth glide and you don't have any catches along the way. You should also use some tiny brackets around the propane fuel tank so that it stays in place, so that it's not moving around. And you as the teacher will want to light that tank, and I would also suggest that you as the teacher, once the students have submitted their model to you, that you're the one who places that model in the ring stand and moves the test stand forward each time. You should also do some practice tests with a fire brick, if you can get one. This fire brick will allow you to see where the hottest portion of the flame is, and that will help you get the correct angle for their rocket models. And then the second part of this, you can see that you can use a paper clip to measure the flame length, and that's the length from the end of the torch to the tip of the inner blue cone of the flame. You also want to have the distance from the tip of the screw to the end of the torch, and that's referred to as the torch distance. Now, as students are building their designs, they'll be using copper mesh as well as pieces of aluminum foil that you provide to them to build their model TPS systems and attach them to the screw using the nuts and washers that are found at the end of the screw itself. One tip I can provide for you in this is make sure that any materials that you buy are not coated with any kind of galvanizing chemicals, because that will produce a noxious smoke. You'll want to find pieces of copper screen that contain no coating, and you can use just regular aluminum foil that you find at the store. I have these cut into 3 by 3 inch sections that the students use to build their TPS or thermal protection systems. They can then attach these to the model at the base using the screw. This last page is the page that students will use to write down their information in a final form. They can use their journals to fill out this page to turn into you, and they should describe the key features of their design as well as what happened during their testing, and provide a sketch of their design that they've drawn and labeled. I hope this helps answer any questions that you may have about the Thermal Protection Systems Engineering Design Challenge, and I want to thank you for joining me today as I wish you luck in doing this activity with your students.